All right. Well, welcome back for the fifth and final installment of LLM Intuitions. And this one's called Language Models as General Problem Solvers. So, if you've been with me the whole way on this adventure, I'm sure by now you're asking, are we there yet? And the answer is no, but we're close. So, in the last video, we talked about transformers and this concept of paying attention and how that removed um, two information bottlenecks. For one, it allowed us to process much longer sequences of tokens, and also it allowed us to contextualize our understanding of each token in light of all the other tokens. And in fact, we repeat that process many times to give the model higher level reasoning skills. And so transformers were a quantum leap in neural network capabilities. They happened in 2017. And then just this flood of them came into existence. So BERT and the first GPT, XLNet, there's actually hundreds of these, and they were all transformer-based model architectures that started to crop up. There is a website called huggingface.io, and they like to use that emoji as their icon. And it essentially became the GitHub for transformer models, where researchers would train large transformer language models. They could post them to Hugging Face and share them and fine tune each other's models, and just kind of represents this golden age of for NLP and text processing. It's kind of funny. In 20 way back in like 2012, 2013, image processing had its golden age in some sense with this thing called AlexNet, and image recognition got a lot better. But a lot of people thought that NLP was still kind of lagging behind despite RNNs and word embeddings. It hadn't quite had its golden age heyday like image processing. Well, I think transformers and Hugging Face and all that kind of ushered in this golden age of NLP. And so all of these transformer-based models were cropping up, and arguably they were all LLMs in some sense. They were certainly LLMs in the sense that they were large, and some of them were even larger than the ones that are performing so impressively today. But despite being really large and using the same model architecture, they didn't necessarily exhibit the same paradigm shifting intelligence and utility that we're seeing from the LLMs of today. So, what else happened? What took us from these transformer models all the way to, say, ChatGPT? Excuse me. Well, in 2020, or at least that's when the paper came out, OpenAI noticed something very peculiar about their state-of-the-art model at the time, which was GPT-2. So let's take a look at that. So I guess by this point in the series, I should define what a language model is. A language model is just any model that, given a string of text, can predict the next token. That's kind of the academic definition of a language model. And so you might say, okay, is a language model useful then? Good for things like quick compose, like we saw in one of the other videos, autocomplete, and apparently useful for translation, but can it solve all kinds of stuff? That's not so obvious if its core ability is just to predict the next token. Well, what OpenAI noticed was that GPT-2 was able to solve some problems that had never explicitly been trained to solve. So here's an example. Imagine you pass this text in to your model to be read, and then you're going to have it predict tokens. After it's read all this, it'll start predicting tokens, sort of like the Quiq compose reader-writer architecture we saw in the third video. So let's say we pass this in, we say, this movie was awesome, hyphen positive, OMG, it was terrible, hyphen negative. And then we say, the acting was subpar, but overall I liked it. hyphen, and then we just stop. And we say, okay, language model that can predict the next token. What do you think the next most likely token is? And what they noticed was that GPT-2, even though it hadn't been explicitly trained, by the way, this problem is called sentiment analysis, where you take a text and you're trying to analyze, did it have positive or negative sentiment? And what they noticed was that although GPT-2 hadn't explicitly been trained on a labeled data set of positive and negative sentiment texts, that it was able to do sentiment classification solely by leveraging the deep understanding of language it got by training on all that web data and through that powerful self-attention based model architecture. And in some cases, it was solving these problems like on par with models that were dedicated to that purpose. And I have to imagine they were like, whoa, I mean, that's a really big deal that suddenly this thing is exhibiting utility that it was never actually trained to solve explicitly. And so there's a famous paper here that I'll just give a shout out. It was called Language Models Are Few-Shot Learners. So when you hear few-shot, what that means is they gave the model 2 examples, so like a few examples, and then left it for the language model to solve an extra one that they didn't provide the answer for. So few shot is when in your model input, you give it a few examples and then expect the model to kind of, catch on to what you're doing. There's also zero shot where you can just not give it any examples and just ask it a question, and through its deep understanding of language, maybe it has a shot at getting that right too. So this really opened their minds apparently that auto-completion or language model, the ability to predict an next token, could be used as a general problem solver. So now let's just briefly look at what GPT-2 looks like. This is a very simple diagram, but it is true. Although it looks simple, I want to say that GPT-2 is very large and heavy. There's billions of neural network weights making all the computations, both to read stuff in a deep way and to make good predictions. But nonetheless, the understanding we've been building up in this series is sufficient to understand how it works. So here we have our blue box, which is our reader module. In most of our videos, we were using an RNN, but that's now been replaced with a self-attention reader stacked many times. Maybe some other stuff going on in there too, but GPT-2 was primarily just a self-attention based reader stacked many times. And then its output goes into a predict module to predict the next token. So using this sentiment analysis prompt, I guess it's high time I introduced that concept. So in the LLMs of today, the text that you provide that you just want it to read and then start completing from is called the prompt. So the prompt had the 2 examples, which made it a few-shot learning example. And then here's the one that we want the model to do for us. We would, once again, tokenize, encode this, and then read it token by token in our reader module until we've read the whole thing, and then we'd start predicting. And, it very well might predict positive and solve a problem for you it wasn't explicitly trained to solve. And so GPT-2, all the GPTs are called decoder-only transformer architectures. If you remember in the last video, I said the original transformer architecture was for translation, and it had the 2 sides, the one for reading the source document, which was the encoder, and the one for writing the translated document, which is called the decoder. And so GPT-2 is just the decoder half of a transformer model. By the way, it can still do translation. Its view of the world is pass everything into me in your prompt. I will read that prompt and I will predict. And even that is sufficient to potentially do translation tasks. If your prompt says translate this English message to Spanish, the current LLMs are able to do that, all just with the decoder side of a transformer architecture. So that means that GPT-2 and models like it have a text in, text out programming model. The text in is the prompt, and the text out is often called the completion. And as I noted in the first video, GPT-2, but I believe pretty much all of the LLMs of today are using subword tokenization. GPT-2 used an algorithm called byte pair that I believe is still being used in GPT-3 and ChatGPT. And GPT-2 had 50,000 unique tokens. So whenever it entered the prediction module, it would assign a probability to each one of those tokens for its search to pick the next token. And I guess on some levels, this picture kind of conveys, at least GPT-2 was actually kind of simple as far as transformer neural networks go, but very large and computationally intensive and very expensive to train and lots of data involved. Okay, so that was an exciting moment, I'm sure. And then you might wonder, well, okay, what happened between GPT-2 and GPT-3? As they've released more of these models, they've released less and less information. So there's going to be some more kind of guesswork and hand waving here. But I think it's safe to say that GPT-3 was more or less the same as GPT-2, except 10 times bigger and trained on 10 times as much data. And it got better, but it wasn't like mind-blowingly better like what we're seeing in ChatGPT. So kind of what I'm getting at here is that yes, the fact that they're large and the fact that they're trained on a lot of data is important, but there's something else that happened to get us to the LLMs of today. Because at least between GPT-2 and GPT-3, we didn't see quite that quantum leap in intelligence. So what happened is when OpenAI saw this emergent ability in GPT-2 to like solve problems it wasn't trained to, either through few shot or zero shot prompting, I think they made an internal decision to go all in on a process that they call model alignment, which basically means taking a large language model and making it more useful. So sort of making it less of an autocompleter and more of an instruction follower. So what does it look like to do that? Well, they train a core language model in ways similar to what we've been talking about this whole time. And I think that GPT-3 was likely their core language model for ChatGPT. Now, that model knows a lot about language, has a very deep understanding of language, and yes, it can do some few shot and zero shot stuff, but not to ChatGPT's level yet. It was trained on fill in the blank corruption type concepts on massive amounts of data. It's a big network, but it's still more of a language model and not so much an instruction follower. Then, they released GPT-3 to the wild and solicited people to play with it. And a lot of people think that as a byproduct of that, they captured a bunch of interesting prompts or instructions that humans wanted the model to do, some of which it probably could do, and some of which it couldn't, and anywhere in between. They also invested heavily in very skilled data annotators who both wrote prompts and responded to prompts, some of which came in from the public on the internet. I think this was very high quality data annotation, and they created some impressive internal data sets that kind of showed, okay, here's a prompt full of instructions, and here's a really great completion to those instructions. And once they had that data set, and also combining some more cutting edge, newer training techniques, this thing called reinforcement learning from human feedback, but they took their core language model and they align it to make it more useful to become an instruction follower. So it's not so much I can predict the next token on web data anymore. It's more of a model that can take an arbitrary set of instructions and has seen a lot of examples of how humans would complete those instructions. I believe they also did this process where they trained a whole separate deep learning model that could score the outputs of their core language model and assign a score, like basically the score that they think a human would give to that output, by training a model that could at least estimate how much a human would like a given completion to a prompt. That also allowed them to scale up, and they would fine tune the core language model with this separate scoring model, as well as the proprietary data set of lots of examples of instruction following. And so I think that's the key piece, that we had models that were large enough and powerful enough to understand language really well, but to increase their utility and make them instruction followers, they had to go through this model alignment process. And that was kind of the final piece to get us to where we are today, which has sort of redefined LLM. The previous transformer models, I think we could have called them LLMs, but at least right now, LLM implies this much deeper level of intelligence, this ability to complete complex prompts or follow instructions. And that's where this came from, and it kind of harkens back to how data and how you use it is king in machine learning. So we're just going to wrap up here. So ChatGPT and a very impressive model that just slightly predated it but didn't get as much buzz in StructGPT. I think they're architecturally very similar to GPT-3, but it was the additional training data and some fancy fine-tuning mechanisms that aligned those models to make them not just like a autocompleter, but an instruction follower. And, in my first video, I said I wouldn't try to explain or act unimpressed by the utility and intelligence of these things. It's just amazing and awesome. But that's my understanding of how we got to where we are today. And I hope that you found these videos useful, and maybe now when you're looking at the APIs, they might make more sense, or maybe you have a better understanding of why the current LLMs are token-based in their pricing and things like that. So thank you very much for your time. Reach out to Quiq if you have questions about LLMs or how they could maybe be leveraged within your business. And look forward to more content from us. We're going to keep working on this stuff. All right, take care.